we can measure the stopping potential. We know because of J.J. Thomson's work soon before this, the charge of the electron. We know h is Planck's constant, the frequency of the light, and the stopping potential. So if I'm sorry, not the stopping potential. This is the work function of the metal, how much energy it takes to release an electron. So if we can measure, any two of these things and determine the third. Again, work function of the metal is HF0, where F0 is that threshold or cutoff frequency. And also, if we might talk about cutoff wavelength or wavelength, and remember that wavelength and frequency are inversely proportional by the speed of light. C equals F lambda. This is the result. But remember the key here, this is our result, and you might say, so what? It's actually a pretty easy result once you really think about. But once you understand that light has energy HF, and that light comes in these photons, and that what happens is the more photons you get, the more electrons you get, but the higher energy photons you get, the bluer the photons, the higher energy the electrons. Okay, but revolutionary here, remember this was a Nobel Prize, and it did change all of physics for all time from 1905 on, is that light's energy is dependent on its frequency, is dependent on its color, that light's energy is dependent on its frequency or wavelength, right? That light's energy is dependent on its frequency or wavelength, and the intensity just has to do with how much of it you have, but it doesn't increase the energy per photon. And so now when you look at the light spectrum, and this I've sort of implied this a number of times, when you look at the light spectrum, you'll often see the light spectrum drawn like this with increasing wavelength right in that direction, and therefore, because of C equals F lambda, increasing frequency in that direction. But now we know that that means that we're increasing energy in that direction. That light becomes more energetic from red to blue or from radio to gamma rays. Gamma rays are the most energetic light. Radio waves are the least energetic light. And that also means that often, while you might be used to seeing the light spectrum like this, we often swap places and put gamma rays on that end and radio waves on that end to make energy go up in this direction. Do an example or two just to make sure you understand photoelectric effect. Say we've got a potassium surface, and potassium we can look up in a book, has a work function of 2.24 eV. If we shine green light of lambda equals 350 nanometers on it, what is A, the maximum kinetic energy of the photocurrent, right? The electrons that are coming off is called the photocurrent, and B, what is the cutoff wavelength? You'll find that all of these are plug-in problems. You just have to figure out what to plug into. Write down the relationship that if you take the energy you put in, take away the work function it takes just to release an electron, that's the maximum kinetic energy you're going to get out of your electrons. So we're just going to plug into that. HF minus work function, minus phi. H is 6.63 or 6.62, I think 6.63 times 10 to the minus. In Planck's constant. The frequency, well, we're given wavelength of the light that's incident, not frequency, so it's going to be C over wavelength, right? That's the frequency. Frequency is C over wavelength. I guess I could have plugged in numbers. Minus the work function, 2.24 eV. So I should have plugged in numbers there. So it is equal to, plugging in the numbers, and that's equal to, I go on, let's notice a unit thing, so important, and especially in quantum mechanics, but so important in physics in general, units, that we've got energy units of joules here and energy units of EV here. So we do need to remember that there's 1.67 times 10 to the minus 19th. The conversion is 1.67 times 10 to the minus 19 joules is 1 electron volt. And we got to do that conversion. And again, I would convert everything to electron volts so that we end up getting 3.55 eV minus 2.24 eV, so the kinetic energy left for the photoelectrons is 1.31 eV. What is the cutoff wavelength? Well, the cutoff wavelength actually has nothing to do with the wavelength that we're using. We want to know if we turn the light energy down, when will we stop getting photoelectrons? And that's the work function is equal to h times the cutoff frequency, which is hc divided by the cutoff wavelength. You probably caught my error, but this is 1.60, not 1.67. I don't know what I was thinking. I'm a little tired. But what I want to do here is just talk a little bit more about units before I move on, but I don't want to spend any time on it. So just, you can look up or figure out what Planck's constant is in eV seconds instead of in joules seconds. And hc is also a common constant. So you can often just look up, these are things that you need to have access to. You can look it up or you can calculate it. And hc is 1.2 × 10 to the minus 6 eV meters, or you can look it up in joule meters. In any case, doesn't matter. Those are just unit conversions, really. And we can go ahead and plug in order to find 1.2 × 10 to the minus 6 eV meters divided by, I'm just repeating myself. So therefore, lambda 0 is equal to 1.2 times 10 to the minus 6 eV meters divided by the work function, which was 2.24 eV. And so therefore, lambda 0, the cutoff wavelength, is 5.5 times 10 to the minus 7 meters, which is 550 nanometers. Nanometers is a pretty common unit for light wavelengths. So that's the answer to part B.